Okay, guys. So last time in our last class, the last thing that we discussed was a limit at infinity. And I just wanted to remind you of the definition. Basically, whenever we say the limit as x approaches positive infinity of a function equals a number L, all we're saying is that the values of the function f approach this number L whenever x is very big in the positive direction. On a similar note, if the limit is as x approaches negative infinity, then it means that the values of the function approach L, so are very close to this number L whenever x goes all the way to the left in the negative direction. So it's very, very small, okay, in the negative direction. And then, we did some examples regarding this. And by the way, these limits are infinity. This is what we call the end behavior of the function. In other words, how the function behave when x is very big in the positive or in the negative direction at the end of the graph, if you think about it, all the way to the left and all the way to the right. And in particular, if when you take a limit like this, if you do get a number, okay, because you could get infinity, like for example, polynomials, right? You take the end behavior of polynomial functions is either positive or negative infinity. So you will never, the polynomial function will never get close to a number whenever x is very large in the positive or negative direction. But if you do get a number, then when you take this limit at infinity, we say that the horizontal line y equals L, where L is this value of the limit, is a horizontal asymptote of the function. So when you are asked to find horizontal asymptotes of a function, that means that you need to find those two limits, the limit as x approaches positive infinity and also the limit as x approaches negative infinity. If you happen to get a number, then you're good to go. You got your horizontal asymptote. And keep in mind that not always you have the same asymptote on both directions. Let me scroll here to the last example that we did. The last example that we did, we were analyzing the function 1 over 1 plus e to the negative x. And we actually found two horizontal asymptotes for this function because all the way to the right, so when x approaches positive infinity, we get that the limit is positive 1. So that will give you the line y equals 1 as a horizontal asymptote. But if you go all the way to the left, in other words, when x approaches negative infinity, we found that the limit was 0. So like once again, the x-axis, which is the line y equals 0, is another horizontal asymptote. Okay? All right. So and then we talked about rational functions in particular, and then we saw that to find limits at infinity of rational function is actually pretty straightforward. It just depends on the degrees of the numerator and denominator, as we can see here in these three examples. So when the degree of the top, looking at the first example, part A, we saw that whenever the degree of the top is less than the degree of the bottom, we can play this trick of factoring the highest power in the top and in the bottom and then simplifying. And then it turns out that all the x's that are responsible for the infinity in the top disappear after simplifying. And therefore, when you take the limit, we get 0 because in the bottom, we still have an x that survives that gives you infinity, namely this one down here. That one survives, okay, which is this one. And then that's why we get infinity. So a number on top over something that's growing very big, the fraction goes very small, so we get 0. So when the degree of the top is less than the bottom, the limit is 0 as x approaches infinity or negative infinity. Notice that if it would have been negative infinity, the same idea will apply. The other situation is, okay, what if the degrees are the same? So if the degree of the top is the same as the bottom, that would be the case like example B. In this case, we can apply the same procedure, and this time the x's responsible for the infinity, they both cancel out in the top and bottom. So what will remain is whatever numbers we had as coefficients of those x's. So in the top we had a 2, in the bottom we had a 3, so that limit was the ratio of those two numbers, 2 over 3. And by the way, in these two cases, A and B, we do have horizontal asymptote. In the first case, the horizontal asymptote is y equals 0. In the second case, the horizontal asymptote is y equals 2 over 3. Once again, if it would have been as x approaches negative infinity, the same idea applies, and we will get the same result, okay? And then the other case when it comes to a rational function is when the degree of the top is bigger than the bottom, okay? Like part C. In this case, when this happens, what's going to happen is that when you factor out the highest power in the top and in the bottom, after simplifying, the x responsible for the infinity in the denominator is gone, but there is an x, at least one x, there could be more depending on the degree on top, but there is at least one x in the top that survive that will still give you some type of infinity, the positive or negative infinity. So therefore, when you have infinity divided by some number in the limit, it's still infinity, okay? So when the degree of the top is bigger than the bottom, we get either positive or negative infinity. How do you know which one is it? Well, you have to see, what's the degree of the x that survive in the top. Also, the sign of the coefficients enter here into play. They are important because, as you know, if you multiply to negative, you will get a positive, and so on and so forth. But the point is that you will either get positive or negative infinity, and therefore there is no horizontal asymptote in this last case. As I mentioned in class, I'm gonna, there's a theorem that summarizes this that you saw it back in pre-calculus. I want to write it again. We left a space, so we wouldn't use time on that one. So let me go ahead and write it now before we move to another idea. So again, this theorem is going to summarize what I just explained here for rational functions. Okay. So theorem. This is basically the end behavior of rational functions. Remember, rational function is a function that looks like a fraction, but the top and bottom, they're both polynomials, okay? So let f of x equals p over q be a rational function. So what that means is that both p and q are polynomials. So pq are polynomials. And let me specify this a little bit more. In other words, our function f looks as follows. The top is a polynomial that has some degree. Let's say the degree is n. So let's say it has the form a times x to the n plus a bunch of other terms, but all of those terms, they have degree less than n, right? Because the leading term will be a times x to the n. So I'm going to write here plus lower degree terms. Remember how we call it last time? We call this like the garbage or the trash. Like these terms, they don't matter at infinity. When we look at the end behavior, what matters is, as you know, the leading term. And then let's say q has degree m. So it will be b times x to the m plus, once again, lower degree terms. So let me say here n is the degree of p, of the polynomial p, and m is the degree of the polynomial q. Okay? So, and as we saw above, the point is that if you want to take the limit as x approaches either positive or negative infinity, all we have to do is look at these degrees here, these numbers n and m, and depending how they compare is the result. So I'm gonna write that down. Now I'm gonna write it for as x approaches infinity, positive infinity, but of course, same thing will apply when x approaches negative infinity. Okay. So then the statement is the limit as x approaches positive infinity, and I'm gonna put a minus here just to indicate that it could be the positive or negative infinity. Okay, what I'm saying here applies to both situations. So the limit when x approaches any of these two infinities of the function f, what is this? Well, it depends, right? What it depends on? Well, it depends on the degrees. So it could be that n is less than m. In other words, this is the case in which the degree of the top is less than the bottom. Or it could be the degrees are the same. Or it could be that the degree of the top is bigger than the bottom. Those are the three situations. So in the first case, so if the degree of the top is less than the bottom, then this limit is going to be 0, right? If in the second case, when the degrees are the same, then the limit is a over b. So it's the ratio of the leading coefficients. And in the third case, in which the degree of the top is bigger than the bottom, then the limit is either positive or negative infinity. Which one is it? Well, you have to decide depending on the sign. So here, this plus or minus, this depends on the signs, on the sign of a over b, and also the degrees. Okay. So in particular, on this note, we can use what we call, the garbage rule that we call it last time. So in this last case, it's important to know that, I guess, let me make a parenthesis here. So for this last situation, remember that when you take the limit as x approaches positive or negative infinity of the function, we can ignore the lower degree terms, the garbage, and just look at the ratio of the leading terms. Now, because the degree of the top is bigger than the bottom, we are in the last situation, then that means that you can simplify this and there will be x's left over in the top. So this is the same as this power function, a over b times x to the n minus m, okay? Because n is bigger, then n minus m is actually a positive number. And then, whatever the n behavior is for this power function, that would be the n behavior of our polynomial, of our rational function. And as you know, it depends on the degrees, right? So whether this difference here is an odd or an even number, and also you have to look at the sign of a over b. That would tell you whether you will get a positive or negative infinity, combined with the degree, of course. Okay, so again, it's pretty straightforward to find the limits of rational function at infinity. Just look at degrees, and then you will be able to quickly tell what the answer is. In the first two cases, that means that we have a horizontal asymptote. So I guess, let me say here. So, okay, this column is for existence of horizontal asymptote. So in the first case, the horizontal asymptote is y equals 0. In the second case, the horizontal asymptote is a over b. In the last situation, there is no horizontal asymptote. Okay? All right, so that's what we discussed last time. Now, before I move forward, I would like to do an example, again, of limits at infinity, of functions that appear to be similar to rational functions, but they're not actually rational because there are radicals involved, okay? And you have some of these problems like this in the homework. I want to make sure that you see a couple of examples here so you understand how to deal with those problems, okay? The point is that the idea is exactly the same as what we follow here. Remember, how did we do these limits at infinity of rational functions? Well, the idea that we used was that we factor out the highest degree, the term with the highest degree in the top and in the bottom, simplify, observe what we got, and then we were able to compute the limit. Well, we're going to do the same thing, okay? That same idea applies here as well. So let me do a couple more examples before I move to another topic. So find the limits. Let's see, let me write here the problems that I want to discuss. Let's say that we do the limit as x approaches positive infinity of square root of 2x squared plus 3x minus 5 over 7x plus 1. So notice that, this may, so, it has the appearance of a rational function, but it's not because of that square root that we have in the top, okay? If we didn't have square root in the top, yes, it would be a rational function. But we deal with this in a similar way. It's just that there are some little details that we need to discuss now. That's why I'm doing this. Okay, so the first one was as x approaches positive infinity. Now let's do one as x approaches negative infinity. of 12x minus 3 over the square root of 9x squared plus 7. And then let me put one that has a higher degree. So let's do 2x squared plus 3x minus 1 over the square root of 5x to the 5 minus 2x cubed plus x minus 2. Okay, so let's do these exercises. 2x cubed. Okay. All right, so solution. So before I do the solution, let me actually point out a little remark, okay? And this may look silly what I'm about to say, but is oftentimes overlooked, okay? And here is the question. What is the square root? Okay, I was gonna use another letter, but let me use x, but it doesn't really matter what letter I'm using here. But here's a little question. What's the square root of x squared equals to? Okay, what is this equal to? And many people will say, or probably the first thing that may come to your mind is, oh, this is equal to x, because the square root cancels the square. But you have to be very careful. Remember, the square root function, the range is from 0 to infinity. In other words, when you do a square root of something, the result is always positive. You will never do the square root of a number and come up with something negative as a result, right? Because actually this symbol stands for the principal square root, okay? So when we say square root of 9, the answer is 3. It's not negative 3. It's true that negative 3 squared will give you 9 as well, but when we use this symbol, the radical symbol, we are actually asking for the positive version of the root, okay? So whenever you have the square root of x squared, because you have a variable here, we don't really know what x is. Since we don't know, x could be positive or negative. So our job is to make it positive. And how do we do so? Well, we put absolute values around. Just to give you a quick example. For example, everybody knows square root of 4. Well, let me write as 2 squared. So square root of 2 squared. Okay, this is 2. That's fine. We don't really need to put the absolute value, but if you want, you could put it. Because after all, absolute value of 2 equals 2, right? But what if, imagine that you did it without the absolute values in general. What if you have this problem? How do you evaluate this? If you go ahead and you blindly just cancel the square root with the square, then you will write this. But if you write negative 2, then you are in trouble because once again, the square root of something cannot be negative. So our job is to put the absolute value, which is going to give us 2. Now, is this the expected answer? Yes, it is, because actually the way that we would do this is before we cancel, we first do the square. That square is going to get rid of the negative. So this is just square root of 4, which now, as you know, is 2. Okay? So, moral of the story. When you do the square root of a variable square, it's okay to cancel the radical with the square inside, but you need to understand that the answer that comes up is positive. If you don't know what x is, you have to put an absolute value around. Okay? This is going to play an important role in our limits in the top, okay, in these examples that we have here. In particular, that will be very, very important for example number 2, because we're dealing with negative x's. Notice that we are going x approaches negative infinity here, okay? When x approaches positive infinity, this is not really a concern because x is positive anyways, and as you know, when when you do the square root of x squared, if x is positive, the answer will just be x, because absolute value of x will equal x in that case. But the sort of point is when x approaches negative infinity, it is negative, and therefore you have to be careful. Okay? All right, so let's go ahead and let's do the problems. So the first one is limit as x approaches positive infinity of this square root over 7x plus 1. And then later and after we do these examples, then I'm gonna come back and I'm gonna give you some insight on how you can actually do this in a similar way of how we did rational functions. But let's do this first. Okay, so the first thing is that clearly something needs to be done here, because if you take this limit, notice that the stuff inside the square root in the top goes to infinity, right? When x approaches infinity, that limit goes to positive infinity. The square root of infinity is still infinity. So this is an infinity over infinity situation, okay, in the determinate form. Something needs to be done. What do we do? Exactly the same thing that we did with rational functions. Let's factor out the highest degree term in the top and in the bottom. The point is, in the top, we're doing it inside the radical. So inside that square root, I'm going to factor out x squared. And then what's left is 2 plus 3 over x minus 5 over x squared, as you all know. And then in the bottom, okay, so I'm going to factor out, let's see, do I want to, yes, okay, let's factor out the x. And then what's left is 7 plus 1 over x. Okay, so we're almost ready to take the limit, but not yet. We still need to do something. For example, I would like to do something about this x here, which is responsible for the infinity in the denominator. And I need to do something with this term here, because that one is this x squared inside the radical is responsible for the infinity in the top. So to do that, let's simplify this a little bit more. So this is the limit as x approaches positive infinity. Now in the top, notice that we have x squared times the parenthesis inside the radical. As you know, we can break this as 2 square roots, right? And then we're going to have outside the square root of x squared. Using the remark that we just discussed, when you do the square root of x squared, an absolute value comes up, right? After simplifying. So this is equal to absolute value of x times the square root of the stuff in the parentheses. Okay, and then over this. A couple of steps are needed here. So now, before we take this limit, we need to make an observation on what's going on with this absolute value. Okay, so remember, we don't want to have that absolute value there, so we need to get rid of it, because once we are out of that absolute value, we can cancel the x in the bottom. The question is, do we need to put a minus on top or not? Because remember, what's absolute value of x? Put it here. Remember that absolute value of x equals x itself if x is greater or equal than 0, or negative x if x is less than 0. Okay, so this is the recipe of how you eliminate absolute value. You can get rid of it, but before you do that, you need to know the sign of what's inside, because if it's negative, you have to put a minus in front. Anyways, the point is that here x approaches positive infinity. In particular, this is telling you that x is positive, right? So absolute value of x is really just x. So we can just rewrite this problem now without the absolute value, because x is positive anyways. And now we are in business, okay? Because now we can simplify this and we can take our limit. And as you know, all those little fractions with x's in the bottom, they will go to 0 when x approaches infinity. So this becomes 0, this one becomes 0, this one goes to 0. So in the top, what survives? The square root of 2, and in the bottom, what survives? 7. So the answer to the first problem is square root of 2 over 7. Okay, so let's do number 2. So for number 2, we have a limit as x approaches negative infinity of 12x minus 3 over the square root of 9x squared plus 7. So notice now that in this case, the main feature is that we are taking the limit as x approaches negative infinity. Okay, so we're gonna proceed as usual, just as we did above. I'm gonna factor out the highest degree term, and so you get 12 minus 3 over x in the top, and then in the bottom we're gonna have 9 plus 7 over x squared in the parentheses. Okay, so again, when you do the square root of x squared, absolute value comes out. So in the top, we're gonna have, let me rewrite the same thing in the top. Then in the bottom, we're gonna have absolute value of x times the square root of 9 plus 7 over x squared. Okay, so now this time we want to eliminate the absolute value, but for that we need to know what's going on with x. Is it positive or negative? Well, this limit is as x approaches negative infinity. So in particular, this tells you that x is less than 0. Okay. Therefore, if we eliminate the absolute value, what do we need to do? We have to put a negative, right? Because when x is negative, the absolute value of x equals negative x. So this will equal the limit as x approaches negative infinity of x times 12 minus 3 over x, and then in the bottom I need to put a negative x. Okay, so that's what you need to be careful about. Okay, so now we're free to simplify the x's, but notice that there is a negative one that remains there, right? Now we take our limits. This goes to 0, this one goes to 0 as well. So on the top, a 12 survives, so let's get in the top. Then on the bottom we have a negative square root of 9, which is 3, so that would be 12 over negative 3. So the answer here would be negative 4. Okay, by the way, the first example, what we just did means that we have a horizontal asymptote for that function, namely the line y equals square root of 2 over 7. In this second example, we also have a horizontal asymptote for the function, namely the line y equals negative 4. Okay, so let me do a third example here. As the limit as x approaches positive infinity of 2x squared plus 3x minus 1 over the square root of 5x to the 5 minus 2x cubed plus x minus 2. Okay, so I'm gonna proceed as usual. I'm gonna take I'm gonna factor out the higher degree, so take out a square, it's 2 plus 3 over x minus 1 over x squared. And then here we're gonna have the square root of x to the 5, then times 5 minus 2 over x squared plus 1 over x to the 4 minus 2 over x to the 5. Okay, so now here in this case, because we have the square root of x to the 5th, right? Once again, here x is approaching positive infinity, so x is positive. But the point is that what we can do is the following. We can, well, the same thing that we have been doing. Let's just split. And then this would be a square root of x to the 5th. I'm going to write that as x to the 5 over 2. So remember, when you have a rational exponent, that just means that you have a radical, and the denominator of the exponent is the index of your radical. Because we have a square root, that means the denominator is a 2. Okay? X to the 5 over 2, and times the square root of, so what is this? 5 minus 2 over x squared plus 1 over x to the 4 minus 2 over x to the 5. Okay, so now when we combine, we need to, subtract the exponents. Now, to simplify these two terms, x squared and x to the 5 over 2. Now, when you subtract 2 and 5 over 2, so 2 minus 5 over 2 is negative a half, right? 5 over 2 is 2.5, so it will be negative 0.5. But then I'm going to bring it to the bottom, positive. In other words, this is the limit as x approaches positive infinity. Now, the x squared is going to disappear from the top, but in the bottom, we're going to have an x to the 1 half, or namely a square root of x, okay? But the point that I want to say is the following. Write all of this. Notice that, it's really a pain to be writing all of these terms with the little fractions because anyways, they don't matter. They will go to zero in the limit. So, after doing this, then we're going to show you how we can do this super quick using the so-called garbage rule. But of course, I want you to see it this way first because this is, the proper way of doing it. But since all of those lower degree terms don't matter, why do we need to keep writing them over and over again? We're taking a limit. But okay, let's go there first. So now we're gonna take our limit. So again, all of these little fractions, they go to zero. But then what's gonna happen is that in this limit, the top up is going to approach 2. But what happens in the bottom? The radical piece is gonna approach the square root of 5. But then we have an x to the 1 half, which is a square root of x. If x approaches infinity, this term right here is gonna go to infinity, right? So at the end of the day, what we're gonna have is a number on top, namely 2 in this case, divided by something that's growing bigger and bigger. It's going to infinity. And what's the answer here? 0. Remember, 2 over infinity, that's 0. If I would have changed the function and had my radical on top and the polynomial in the bottom, then the square root of x here that survive after simplifying this one will be in the top, right? So we'll have infinity in the top, and then the answer would have been infinity instead of 0. Okay, so you have to see, what comes up after you do your simplification. Okay, so let me quickly illustrate this using the so-called, some people call it the garbage rule. And remember, this is the fact that uh, lower degree terms don't matter. That's what we want to exploit. Lower degree terms don't matter at infinity. Okay, so let's redo the 3 problems, but it's gonna be more quicker. Okay, and from now on, I'm gonna be doing this. Okay, whenever a problem like this comes up, I'm gonna use this garbage rule because it's really convenient and fast. So when you do the homework, if you want, first make sure that you understand this proper way because this is the proper way what we just did here, but it's too long. We're writing too many stuff that we don't really need. I mean, all of these things that I'm writing here, they go to 0. So we know they're not gonna matter at all at the end. So why carry that over and over again? Okay, so let me just rewrite the problem. First one that we did. Then, this limit is just, we're gonna discard the lower degree terms. In this case would be these guys and this guy. Okay, we only stay with the leading terms. Okay, so in the top we have square root of 2x squared over 7x. And now this is an easier limit to compute, right? Because again, this is the limit as x approaches positive infinity. Now square root of x squared, as you know, is absolute value of x. I mean, I'm not gonna repeat the whole thing. It's absolute value of x, but because x is positive, we're going to negative infinity. That's just x. So this becomes square root of 2 times x, and then over 7x. These guys cancel, and then we see our answer as square root of 2 over 7 because a constant remains, and the limit of a constant is just a constant. Okay. So for the other one, it was as x approaches negative infinity of 12x minus 3 over the square root of 9x squared plus 7. Again, using our garbage rule, we discard the negative 3 on top, and we discard the 7 in the bottom. Now simplifying, notice in this case that x is negative, so when we take out the x squared out of the square root, we have to put a minus. It comes out as a negative x, okay? Because of the absolute value, and to eliminate the absolute value, because x is negative, you have to put a minus in front, okay? We know all of that already. No need to repeat it. So we're gonna have, that would be 3x, but remember, we need to put the minus because of the x. The square root of x squared is negative x, and the square root of 9 is 3, so negative 3x. The x is cancelled out, and then 12 divided by negative 3 is negative 4. Okay, so we obtained before. And finally, for the last one, again using our garbage rule, we can fit the problems in one line. Before we had to write a lot. Now, the more that we need to write is at the beginning writing the whole problem. And the rest is straightforward. Okay, plus x minus 2. So here in the top, the garbage is 3x minus 1. In the bottom, the garbage is the negative 2x cubed plus x minus 2. Okay, and that will be gone. So limit as x approaches positive infinity, 2x squared on top, and then the square root of 5, x to the 5 in the bottom. And then once again, this just means this will be limit as x approaches positive infinity of 2x squared over square root of 5 times x to the 5 over 2. And as you know, we simplify the x squared with the 5 over 2, but then a 1/2 remains in the bottom. So this one takes an extra step because of the simplifying process, times x to the 1/2. And then when you take that limit, the bottom is infinity, so it gives us 0. Okay, let me write this better. Square root of 5 times, and then x to the 1/2, or square root of x. Or if you want, you can just write square root of 5x. Many ways to do that. Okay. Actually, let's see. Let me do it. Okay, I did it this way on top. Let me show you another way, which is probably maybe what you're used to when simplifying radicals that you learned before. Basically, what I want to do is, let's go ahead and let's simplify this radical. Okay, so let me write it here. So square root of 5x to the 5th. As you know, to simplify radicals, what you do is you need to look for, powers that are multiples of the index, so you can take them out. So in this case, there is nothing you can do with the 5, but then the x to the 5, we can write it as x to the 4 times x inside the radical. Why did I do that? Because my index is 2, so 4 is a multiple of 2, so I know I can simplify x to the 4 and take it out. So this is going to come out as an x squared, right? Square root of x to the 4, that's an x squared. No need to worry about absolute values here because the square is positive anyways. And then the 5x stays inside. Okay, so that's how you can simplify this radical. So we can do that, and then that would be better. So I'm talking about this guy. Give us this, okay? So then square root of 5x to the 5 is equal to x squared square root of 5x. Now the x squares cancel nicely, and then you can see that we have a 2 on top, and then that x in the bottom will give us infinity. Square root of infinity is still infinity. So then we can see the answer is it. And it looks a little bit cleaner than, subtracting the exponents and that 1/2 and so on. Okay, So notice that it's very similar to the way that we treated rational functions, okay? It's just that you have to keep in mind that there is this radical, so there are some subtleties that you have to be careful about, okay? All right. So yeah, this is what I wanted to say about this, okay? About limits at infinity. By the way, well, we can see here that these three functions they have horizontal asymptotes, right? Okay. So now let's talk about another theorem. This theorem that I'm about to discuss is very special because this theorem will allow us to compute limits of functions that otherwise we wouldn't be able to, by conventional means, like using algebra or tricks or just analysis like the one that we're doing here. Okay? So what I'm talking about is the so-called squeeze theorem. And it's actually, a very natural idea to consider. And so let me show you what I mean. So as a motivation, here is the question that we would like to answer. So for example, remember that at one point we saw the function y equals sine of 1 over x, right? And then we tried to analyze the limit as x approaches 0. We did it from the right, but then, it doesn't matter. But in this case, we did it from the right. So let me put exactly the example that we did. This was the very first day. And then we figured out that this limit actually does not exist, right? When you get close to 0, this function starts behaving crazy and it doesn't get close to any particular value. We actually found a sequence when you get close to 0 with this sequence, then the values of the function are either 1 or -1. And the point is that when x approaches 0 from the right, 1 over x approaches infinity, as you know now. And that means you're going all the way in the argument of the sine function. The argument is going all the way to the right in the x-axis. And as you know, sine is a periodic function, so it's always oscillating. And it will take on every value between 1 and -1. Keeps going this over and over again non-stop. So it doesn't get close to anything specific. That would be a quick way of realizing why the limit does not exist. But now, a question is, okay, we know that limit does not exist, but how about the following? How about the limit as x approaches 0 of the function x squared times sine of 1 over x? Okay, how about this limit? In other words, because the limit of sine of 1 over x does not exist in this situation. But how about this function? Here we cannot use the property that the limit of a product is the product of the limits, just because, yes, x squared is fine, but sine of 1 over x is not. That limit does not exist. So we cannot separate these as two limits. So we would like to say something about this function, okay? And none of the tools that we have discussed so far will allow us to say something about this. And that's why, we have to look at another idea. And that idea is the squeeze theorem. It's actually a pretty straightforward idea. Let me just uh, draw a picture to show you what's going on, and then I'm going to write the statement. Okay, so here is the situation. Suppose that you have uh, three functions, okay? There is one function, which is the one that you are interested, okay? But this function, you cannot really control how it behaves. You don't know how it behaves. Let's call that function f, okay? So I don't know. I'm just gonna write something here, whatever. So let's say this is a function f. It's a function that, I mean, this picture that is not showing that the function is becoming crazy or something. But imagine that this is a function that at x equals a, or around a, let's say a is here, is a function that behaves like crazy. Like you have no idea what's going on between these functions, for this function around a. And of course, what we're trying to figure out is what's the limit as x approaches a of f of x. Okay, we're trying to figure this out. Again, this was a nice function what I just draw, but for example, the function x squared times sine 1 over x, it behaves very crazy around 0. Okay, but let's see, is it really that crazy? Well, we're gonna be able to answer that question soon. So let's say that we have a function and we are interested in what happens around a for this function, but we cannot just analyze the function itself. But now we need more data. So what if I tell you, let's say now that we also have two more functions, let's call them g and h. Let's say that we have a function h that's always above the function f, okay? And then we have another function, let's call it g, that's always below the function f, okay? Let's call it g. Or it doesn't have to be always, but at least around a, so around a, around x equals a, they satisfy the following. The function f is always bigger than g and less than h. Okay, so the function f is between these two functions g and h, around a. Away from a, I don't really care, but around a, this inequality holds. And even though we don't know what happens with f, let's say that we know what happens with g and h. So g and h are nice enough that we know their behavior around a. In particular, we know their limit. So let's say that the limit of the function h, so that let's say that the limit of the function h is some value, let's call it L. Let's say this point, this value is L. And let's say that the limit of the function g is also L. So both the big and the small function, they both have the same limit around A. What do you think is gonna happen to the function that's in the middle? Which could be a very bad function, something that's behaving, very crazy. Let me attempt to do something more crazy for f. Okay. The point is that because f is always between h and g around a, the moment that we get closer and closer to a, this function f is being squeezed between the two, h and g. So if h and g go towards the same value in the limit, the ones that's in the middle is forced to have the same value as well. Hopefully you understand this. Okay. In other words, if the limit as x approaches a of the function g equals a number L, which happens to be the same limit as x approaches a for the function h, then our function f has no other choice than to approach the same number. This is called squeeze theorem. Okay? So if you have a function that's between two other functions around a point, and if the outside function, the small and the big one, they both have the same limit, they approach the same value when x approaches a, then the middle function, the one in the middle, has to approach, the limit exists and it approaches the same value as well. Okay, that's the statement. And hopefully the picture kind of helps you, understand this. So we call this a squeeze or sandwich theorem. Some places they call it the sandwich theorem because the function in the middle, is like, so I guess G and H are the bread and F is, I don't know, whatever you like on your sandwich, that's what you put in there. I don't want to say something specific because, some people don't like meat and that kind of stuff. Anyways, that's why we call it sandwich. Okay. F is your favorite topping and G and H are, you know, the bread, the top and the bottom of the bread. Okay, so let me put the statement. So theorem, so squeeze theorem. I'm just gonna rewrite what's above, but a little bit more formal. Okay, so squeeze theorem. This is a good tool to know to compute limits. And the challenge is, of course, that typically when you have this problem, when you want to use squeeze theorem, you only know the function f because that's the one that you want to find the limit of. Nobody's gonna tell you what's g and what is h. Your job is to find these two functions, this g and this h, such a way that they have the same limit. And then you can use squeeze theorem to deduce the limit of f. That's what makes it a little bit complicated sometimes. But for example, in the cases above, it would be very straightforward because every time the sine or cosine show up, we already have a very good starting point to use. So we take advantage of that. You're gonna see what I mean in a second. Anyways, so squeeze theorem. Here's the statement. So suppose we need three functions, right? So let f So let f, g, and h be three functions such that for all x in an open interval containing a, for all x in an open interval containing the number a, we have, in other words, this is, so when I say in an open interval containing a, what I mean is around a. That's just a fancy way of saying, so that around a, okay, we have the following inequality. We have that f of x is between the function g, the function h, okay? So we have three functions satisfying this condition around a, okay? And again, at a, as this is except possibly at a. At a, we don't care what happens. Remember, the whole point is around a. So the for all x in an open interval containing a, let me say here, except possibly at a itself. Except possibly at a. So as long as around a, we're good. Except possibly at a. The functions of the for all x in an open interval containing a, we have, okay, no comma here. So B3 functions of the for all x in an open interval containing a, we have this inequality, and also assume, so we have this, and if the limit as x approaches a of the function g equals the limit as x approaches a of the function h, if they both equal a number L, so if the small and big function, they both approach the same limit, then the conclusion is then our function f must have the same limit as well. And the limit as x approaches a of f of x exists and equals L. Okay, that's the so-called squeeze theorem. Okay, so again, refer to the picture above. It should be very straightforward. So as I mentioned, in general, the difficult part is to obtain these two functions, g and h. Okay, so but in some cases, it's not that difficult. Let me do as an example. Let's solve the question posed above. For example, number one, say that I want to find the limit as x approaches 0. Oh, by the way, and this statement that I am saying about Squeeze theorem, it also, of course, applies. Let me write down the remark. It applies if the limit is at infinity. It doesn't have to be at x equal a. It also applies at infinity, and it also applies for side limits. Okay. So let me write that down. So remark. This theorem also applies to limits at infinity, to limits at infinity, what's going on with my pencil? Doesn't want to write. Why? No battery? What's going on? Okay, give me a second because now my electronic pen is not behaving good. I'm not sure if it is the pen or if it is the software. So let me check. Let me just restart this and then see. Okay. So when something is giving you an issue, just close it and then open it again and see if that solves the problem. Or if it is an electronic equipment, turn it off, wait a little bit, then back on. Sometimes the issue is gone. Okay, so this theorem also applies to limits at infinity. That means if a is either positive or negative infinity, to limits at infinity, and side limits as well. Okay, because I don't want to write the same statement like I guess 3 more times or 4 more times to positive infinity to negative infinity and to the right of a and then to the left of a. Okay, so all type of limits, Squeeze theorem is valid. All right. So having said that, then let's do this our first example. So let's do this one: x squared limit as x approaches 0 of x squared times sine of 1 over x. Okay, you know this is just a new tool that we just learned, Squeeze theorem. So you approach a problem like this, the first thing that you do is, okay, try to plug in. We know that plugging is not going to help us because we get 0 times something that does not exist. So the question is, what is this? Well, we don't know. We need to analyze it. Okay. Then, none of the techniques that we have discussed will help us here. There's no factoring, nothing really that we can do. So let's try Squeeze theorem. And why Squeeze theorem seems like a reasonable choice? Because we have this sine function. And remember, this is our middle function, x squared times sine of 1 over x. This is our f in the statement. That's our f. Our job is to find g and h. So somehow we need to be able to build this inequality. Okay? But sine will always give you a starting point. So note, what do we know about the sine function? We know that regardless of what's going on, the sign is always between 1 and -1. So this is going to give us the starting point. We know that I don't care what x is, sine of 1 over x will be always between -1 and 1. This gives us a head start. Now we just have to, build our function. So what do we need? We need x squared times sine of 1 over x. So let's multiply everything by x squared. We can do that. So multiplying everything by x squared, then it's going to give us the negative x squared. Notice that x squared is positive, so we don't have to flip any inequality. You have to be careful because when you're dealing with inequalities, if you multiply by something negative, remember, you need to flip the direction. Okay, after multiplying the entire inequality, the compound inequality in this case by x squared, we obtain this. So our function of interest, which is x squared times sine of 1 over x, turns out is actually between these two other functions, between the function negative x squared and the function x squared. Okay, so now what remains for, so we found the inequality that we needed, right? This inequality is actually always true. Now the question is, does it work for us? And for this to work, remember, it's not just having the inequality. We need to have also the condition that the limit of the outside functions, they have to match. Do they? So let's see, I like to always do the little diagram that I did at the beginning. So the outside the smaller function, what's the limit of this as x approaches 0? Why 0? Because that's the one that we're analyzing, right? X approaches 0. Here it is. Okay, the limit of negative x squared as x approaches 0, that's 0. How about the outside function, the big function, x squared? Well, that is also 0. because the small and big function, they both have the same limit as x approaches 0, then the one in the middle has no other choice to go to the same place. So what is this limit? This limit is 0 by the squeeze theorem. And the justification is right here. This little picture this little diagram that you see here is enough to justify. Okay. All right. So let's see. Before we move on, let me actually show you uh, what's going on. So what this means is that we have, if you think about the graph, so we have the function x squared over here. This is y equal x squared. And then we have this our function h, right, the big one. Then we have our function negative x squared over here. And what happens is that our function f, I don't know, is doing something, but it's behaving crazy, but it's when it gets closer and closer to 0, because it's always trapped between these two parabolas, it has to behave good. It has no chance of doing whatever it wants, because the x squared and the negative x squared squeeze the function towards 0. When x is very close to 0, the y values have to get squeezed towards 0. Okay, so that's more or less what's going on here. Let me actually bring up Desmos and let's give it a try. Let's show a picture so you can actually see what I'm talking about. I mean, it's gonna be a better picture than what I just drew here. So let's see, we have go here, Desmos. Okay, so our function is y equals x squared times sine of 1 over x. This is our function. Okay, maybe. So notice how it wants to behave bad, but when it gets close to 0, it kind of it starts to already behave like a good boy. Okay, anyways, so that's the function that we want to analyze. Let's say that of course, if you already have the graph, then you can tell what's happening. But even if you have your doubts, then let's find the functions that we found. So we found y equals x squared, and then y equals negative x squared. Interesting. And the choice of colors is actually the same. So as you can see, let's see, let me zoom out a little bit. So we have our blue function, okay, that's x squared. We have our green function, that's negative x squared. And the red function is the function that we are interested in. And as you can see, it's between the blue and the green, and particular around 0, which is really what we care about. And notice how the red function is going back and forth, up and down, up and down, but because it's always between the blue and the green, as the blue and the green get closer and closer to 0, the y values are close to 0. So the one in the middle, the red, even though it may want to behave bad, it has no choice. Look how it's being super squeezed between the two, and then eventually it has to converge to the same point. It has to have the same limit as the big and the small function. Okay, so as the squeeze theorem in action. And actually notice that we could have done the same thing if the function would have been x times sine of 1 over x instead of x squared. Okay, the same idea will apply. It's just that you have to be careful, because when you move, this would have been an x instead of having a square here. Let's say that we had an x, just x. You do the same thing, multiply both sides by x, but technically you will need to make a note, because since we're approaching 0, if you do it from the right, x is positive, so nothing happens with the inequalities. But if you do it from the left, then x is negative, so you will have to flip. Okay, But at the end of the day, you're going to end up with the same idea. The point is that if you multiply by x, if it was an x instead of an x squared, then you're going to have your function. Our function will be trapped between negative x and x. Okay? And once again, both of those will go to 0, so our function will also go to 0 as well. I'm saying that here so that we can modify here in the picture so you can see what I mean. So if I drop the power here, that means our function is going to be between the line y equal x and y equals negative x. So let's drop the power. Okay. So then now we need to modify this because now it's between the line y equal x and the line y equal negative x. So here you go. Here we have the line y equal x, that's the blue one. The line y equals negative x, that's the green. And notice how our function, again, wants to behave bad, but because it's always between those two, at 0, you know, it really wants to be a bad boy. Look at this. But then, you know, you get close to 0, it has no choice to come down and eventually, I don't know when, but eventually it has to go there, as you can see. Okay, it cannot go beyond. Yes. Look at this, is really taking on every single value that it can, but it has to come down eventually. Okay. All right. So enough of this. So hopefully you get the idea. So point is, Squeeze theorem is a very nice theorem, and we're gonna use it today to compute to calculate one of the special limits that we're gonna discuss. Okay. All right. Good. So let's continue. Let's see. Let's do one more example before we go on. So we did this. So every time that you have a limit that you cannot compute directly with any algebraic trick, if the function has a sine or a cosine, you may want to try Squeeze theorem. Okay. Again, the challenge is in coming up with two functions that will bound the function that you analyze. Okay. All right. So let's do limit as x approaches positive infinity of cosine of x over x. Okay, so for this limit, once again, because x approaches infinity, the same thing is gonna happen. The argument of the cosine goes to infinity, so this x over here goes to infinity, and the cosine oscillates, so that limit does not exist. Okay, but let's try to use our common sense here. Whatever happens with x, the top is trapped between 1 and negative 1, because cosine is between 1 and negative 1. And the bottom is getting bigger and bigger and bigger and bigger, because we're going to infinity, right? That x in the denominator goes to infinity. So even though the top is doing whatever it wants, in the sense that it's taking on any value between 1 and negative 1, the bottom is getting bigger and bigger, so the whole fraction has to get smaller. So we're expecting this limit to be 0 as well. And indeed, we can quickly justify this by using Squeeze theorem. So how? Well, again, cosine of x is between negative 1 and 1. Now we're interested in x, so I'm going to divide everything by x. Because x is approaches positive infinity, x is positive, so we don't have to flip anything. Okay. This tells me that x is positive. And now we're interested in the limit as x approaches positive infinity. Now, when x approaches infinity, negative 1 over x goes to 0, and so does 1 over x. Oops. So that means that the function in the middle has to approach 0 as well as x approaches infinity. So this is equal to 0 by the Squeeze theorem. Okay. All right, so we're gonna see the Squeeze theorem in action pretty soon. Okay. Okay, so that was Squeeze theorem. Then the last thing that I wanna talk about are some special limits that you need to have in mind when you are computing limits. Sometimes when they show up, you can use the theorem that I'm about to write. Okay, so special limits. So theorem, I'm gonna prove the theorem. Okay, at least I'm gonna prove 1 and 2 because part 3 is just a definition. So The special limits are this. So limit as x approaches 0 of sine of x over x, limit as x approaches 0 of 1 minus cosine over x, and then the other one is the limit as x approaches 0 from the right of 1 plus x to the 1 over x. Okay, and right, so yeah, that's the limit, and then I'm gonna write a remark. So the answer to number one, you already know it, okay, because you explored this limit or a version of this limit numerically in the homework. Okay, so as you know, this is equal to 1. Okay, second special limit, notice that this is the limit as x approaches 0. So if you try to plug in, you get 0 over 0 situation, okay, which is an indeterminate form. Number two, the same thing. You plug in 0, you're going to get 0 in the top and 0 in the bottom because cosine of 0 is 1. So you get 0 over 0. So this limit turns out is equal to 0. Okay. And the last one, there's another type of indeterminate form that we will study in general later, which is 1 to the infinity. Notice that when you plug in 0 here, you get 1 in the bottom and infinity in the exponent. So 1 to the infinity is also an indeterminate form. This is equal to the number e. Now, number 3 doesn't really require justification because this is just the definition of the number e. That's how we define e. Okay. And I will say something about this when we talk about indeterminate forms and so on. I'm gonna say a little bit more, but in calculus 2, when you talk about sequences, that's when you really are going to understand why this limit exists and is equal to something, which we decide to call it e. Okay. In calculus 2, you will learn that when you study sequences. So right now, this is the definition of the number e. But let me actually do a little remark because this limit, the way it's showing up, is not really naturally how e is defined. So I'm going to make a change of variables, and this way I'm going to show you another technique that you can use when you compute limits. You can change variables, okay? Here is what I mean. So I'm going to do the following. So for number 3, this is about limit number 3. So I'm going to let the letter t represent 1 over x. If I do that, then that means that x is going to be equal to 1 over t. So, for example, the function 1 plus x to the 1 over x, with this new change of variables that I just did, will look like this. 1 plus 1 over t to the t. Okay? In other words, instead of having the fraction in the exponent, I want to have just a nice variable in the exponent. So I move the fraction from the exponent, I move it down, to the parentheses, as you can see, doing this. But then, of course, something else needs to change. We need to change also the limit behavior. What type of limit are we taking? Because I'm calling t, we're going from the variable x to the variable t, like so. So we also need to say something about what happens when x approaches 0. What can we say about t? Well, note what's the limit? So what happens to t when x approaches 0? In other words, what's the limit as x approaches 0 of t? Well, t is 1 over x, so that's going to be positive infinity because x approaches 0 from the right. 1 over 0 with positive numbers is going to be positive infinity. In other words, what we really say is that when x approaches 0, t approaches positive infinity. Okay, so the limit in number 3 can also be written as the following limit. The limit, instead of x approaching 0, I can say t approaches positive infinity, but then I have to modify the function, right? 1 plus 1 over t to the t. And because these two limits are the same, or they was change variables, this is also e. See now, instead of x something approaching zero, now we have something approaching infinity. Notice once again that this is still a 1 to the infinity with the new variable. Okay, take the limit, you still get 1 to the infinity. But this is closer to the way that we define the number e. When you talk about sequences in Calc 2, you will understand. But keep in mind that you can use these tricks, this substitution, to actually compute limits. And I'll show you an example later. Okay. All right. So that was that. In other words, number 3 has, so now since I did this remark, I will say number 3, I'm going to say this. Then I will also say that you can also write the limit. I'm going to use the same variable, but if the limit is as x approaches infinity, then your function has to be 1 plus 1 over x to the x. If this limit shows up, this is also e. Okay? So, and the remark below is just the justification. Okay, so what remains here is to actually justify 1 and 2. Like I said, number 3 is really just definition of the number e. Number 2 follows immediately from number 1. So really what requires a full proof is number 1. Let me prove number 2 first, assuming 1, and then we just focus on number 1. Okay? So proof. So number 2 follows from number 1, and here is how this happens. So proof number 2. We want to take the limit as x approaches 0 of 1 minus cosine over x. Okay, so here's the trick. I'm going to multiply top and bottom by the conjugate of the top, and you will see immediately why I want to do that. Because when we do this, we're going to have the limit as x approaches 0. Now in the top, we have 1 minus cosine times 1 plus cosine. As you know, that's difference of squares, so that becomes 1 minus cosine squared, first guy square minus the second guy square, over this. And the reason why I did this is because now 1 minus cosine squared equals sine squared. Remember trigonometric identity, so recall that sine squared plus cosine squared equals 1. Okay, so 1 minus cosine squared equals sine squared. That's what I'm using. And now we can go ahead and we can separate this. So this is the limit as x approaches 0. I can write this as sine squared is sine times sine. So we can write as sine over x times sine over 1 plus cosine of x. And now we can use the property that the limit of a product is the product of the limits, provided that both limits exist. But the first limit is actually special limit number 1. That's why it said follows from 1. Number 2, sine of x over x as x approaches 0, that limit is 1. And sine of x over 1 plus cosine, that would be 0 over 1, which is just 0. So the final answer here is 0 as expected. All right, let me write the steps. So this is the product of the limits. Okay, and then, this first limit is 1 from number 1, special limit number 1, and this second limit is just 0. When you plug in, you will get 0. You get 0 over 1 plus 1, right? So you get 0 over 2, which is 0. So then the final answer is 0, as expected. 1 times 0, which is just 0. Okay, so really all that remains is to argue number 1. If we prove that number 1 is true, then our theorem is complete. So proof of 1. Okay, so when you look at the function sine of x over x, so we want to analyze the function sine of x over x. So we want to figure out what's the limit as x approaches 0 of sine of x over x. That's what we want to do. Okay, so I'm gonna use squeeze theorem. That's the point. Okay. Now for that, we're gonna rely. I have to come up with some functions, right? By the way, notice that the usual ones are not gonna uh, help us. Okay. So note. Um, so I'm gonna use squeeze theorem. So idea, use squeeze theorem. But if we try to use the usual approach with this, which is to know that sign is between -1 and 1, then divided by x, let's say x is positive. Let's say we're doing it from the right first, okay? This is not gonna help us because when x approaches 0, this guy here will go to -infinity, and this one here is gonna go to positive infinity, right? So not the same. Let's say x is 0, okay? X is greater than 0. So let's say we're doing it from the right first. The point is that that inequality, that is inequality that we get by using the fact that sign is between -1 and 1, is not really helpful because the functions that we obtain, yes, sine of x over x is between these two functions, but they behave differently when x approaches 0, right? Let's do it from the right. So when x approaches 0 from the right, uh, you know, the lower function goes to -infinity, the big function goes to positive infinity. Different values. We cannot say anything about the middle. So this one, well, I don't know. Okay, so we cannot say anything about sine of x over x with this inequality. So this is not good. Now, is there a more clever inequality that we can come up with? Okay, so let's, but for that we need to work a little bit harder, of course. So here is what we do. So we're gonna use geometry. Okay, so of course I'm gonna bring up the unit circle. What else? So we have our unit circle. Okay, let me not label this because I'm gonna be using x as the angle, and so I don't want you to get confused. So let me draw it big, so we have a nice space to draw. Okay, well, I'm having a hard time doing this now. Okay, all right. So 1, 1, -1, -1, and let's say that we have. Remember, we're getting close to x, close to 0. The limit is as x approaches 0, so our angle is very small. The angle that we are analyzing, which is the argument of sine, is a very small angle close to 0. We can do it from the right or from the left. I'm just going to draw the picture from the right, but whatever I do from the right will also apply to the left. Just reflect the picture, okay? You will see what I mean in a second. Anyways, let me just put it here, okay? This is our angle x measured in radians. If you're doing it from the left, then it will be here, and then this will be the x that you look at, okay? So just reflect. Whatever I do, just reflect it if you want to do it from the left. Okay, so we have our angle, okay, and then I want you, uh, okay, so let me continue. So we have this angle, it gives you a point here, okay, then I'm gonna do the following construction. I'm going to draw the tangent line here, perpendicular line to the x-axis, tangent to the circle. So this is a 90-degree angle, and then I'm gonna extend this, okay, and there is a point here. So in other words, that point on top is the point, you drop a perpendicular to the x-axis and it's tangent to the circle at the point 1, 0. So making a 90-degree angle with the x-axis. And also when you extend the radius of the circle, the terminal side of x, it goes towards that point. In other words, we have a big triangle, as you can see. So there is a big triangle here. It's a big right triangle, okay? I also want you to notice that there is another triangle that I want you to consider, which is this one. So there is also a small triangle, which is this one. So blue and yellow makes green. Okay, so There are three geometric figures that I want you to pay attention to. There is a big triangle, the small triangle that I just shaded, and then there is a circular sector, which I guess I'm gonna just shade the part that's here. Let me just, okay, no, that's too. The circular sector is it's like a slide of pizza. Okay, so in other words, is this portion of the circle. Here is x, right? And then you have the radius 1. Remember, this is 1. The radius here is 1. And then this one is 1. And then the circular sector is all of this. Okay? If you're a little pi. Okay? We call this a circular sector. A sector. Or circular sector. Let me say. Okay? So there are those three geometric regions, if you will, that we have in this picture. And I want you to understand that we have a very nice inequality that we can draw now by looking at this. For example, the small triangle, the green triangle, the area of that triangle is less than the area of the sector. Notice how the sector is actually slightly bigger than the triangle. There is that little curvy thing that's more than the triangle. But then the sector itself is less than the big triangle because it's inside the big triangle, as you can see from the picture. So by looking at this picture, it's clear that the area of the small triangle is less than or equal to the area of the sector, which is less than or equal to the area of the big triangle. Okay, so that's an inequality that we get from geometry. Now we just need to figure out what are these values equal to. Okay, let me move this over here. A little bit below. Okay, good. So for the small triangle, we're gonna use a formula for area that you learned back in trigonometry. So notice that the green triangle, we have the angle, that's x, and then we have one side, which is 1, that's the radius, and then this other side is also 1, right? That's another radius of the circle. So we know two sides and the angle in between. And remember that in that situation, let me remind you of the formulas here. So if you have a triangle in which you know this side, this one, and the angle in between, let's call it alpha, then the area of that triangle can be calculated as 1/2 a times b, the sine of alpha. Okay, the typical formula is base 1/2 base times height, so base times height divided by 2, but this is an alternative formula that's useful, because what if you don't know the base or the height of the triangle? But if you know two sides and the angle in between, you can find the area using this formula. Okay, this is something that you discuss in trigonometry. Okay, and since I know I'm gonna need the formula for the sector, let me write it here. Notice that here x is in radians. It's an angle in radians. When that happens, then the area of the sector is, again, you saw this back in trigonometry, is 1/2 times the angle times the radius squared. But because the radius is equal to 1 in this case, so r is equal to 1, r equals 1, so that's just 1/2 x, okay, or x over 2. Okay, so we have that, and then so that means the area of the small triangle, that's gonna be 1/2. Now AB, so A and B, they are both equal to 1 in our case, so that's 1 times 1 times the sine of x, that's the sine of the angle in between. The area of the sector, as you just saw, is 1/2 x, and then the area of the big triangle. Okay, a big triangle is a right triangle. One leg is equal to 1. I don't know the hypotenuse, but I want to know how much is this one over here, this other leg. And for that, let's find the coordinates of that point in the top. So the x value of the point is equal to 1, right? And then what will be the y value? Well, I claim that the y value equals the tangent of x. And indeed, remember that's a right triangle. So what's tangent of x? That's opposite over adjacent. So whatever the opposite is, that's your y, right? And then the adjacent is equal to 1 in this big triangle. So that means that the y value of that point is the same thing as tangent of x. Okay? So this part right here is tangent of x. Okay, so we have that. And then now that we have the right triangle and we know the two legs, then we know that the area of a right triangle is the product of the legs divided by 2, because one leg serves as the height while the other one serves as the base. Okay, so that would be tangent. So 1 times tangent divided by 2. In other words, we have here the non-trivial inequality that sine of x over 2 is less than or equal than x over 2, which is less than or equal than tangent over 2. Multiplying everything by 2, we get this. So we can cancel all the 2's, right? So we get this inequality that x is between sine and tangent. This is a nice, and remember here x is in radians. This is a nice inequality that is actually non-trivial. The value of the angle is always between the sine of the angle and the tangent of the angle. So now that's not really what I want. I want to have sine of x over x in the middle. So I have to work a little bit more. Now remember, tangent is sine over cosine. So let me rewrite it. And so what I'm going to do is, because I want to have a sine, I'm going to go ahead and I'm going to divide everything by sine, because that's going to give me a sine in here. But then I divide by sine here and I divide by sine here, giving us 1 less than or equal than x over sine less than or equal than, so let's see, the sines cancel out and we get 1 over cosine. Okay. All right. So we have this inequality, and okay, I wanted sine over x, but we have x over sine. That's okay. If we know what this limit is, then our limit, we just flip it, because x over sine of x is the same thing as 1 over, so sine of x over x is the same thing as 1 over x over sine of x. So it's going to be pretty easy to do. So now we got this inequality coming from geometry, and the question is, will this do the job for us? Well, let's see. Remember, we're interested in the limit as x approaches 0. Okay, so our function here is the function 1, and the limit as x approaches 0 of 1, well, that's just 1 because that's a constant, right? Then the outer function is 1 over cosine, and the limit as x approaches 0 is also 1 because cosine of 0 is equal to 1. So now we found what we needed, because we have these two functions, the big and the small function. They both approach the same point when x approaches 0. They both approach 1. So the one in the middle has to have the same limit. Okay. So by Squeeze theorem, we have that the limit as x approaches 0 of x over sine of x equals 1. This is what we have proved so far. Now, how do we use that to help us do our problem? Well, we know that the limit as x approaches 0 of the function that we want, which is sine over x, we can rewrite this as 1 over x over sine. Nobody can stop you from doing that. Okay? And now we use the rules. The limit of a quotient is a quotient of the limits. So as long as they both exist, the limit of the top, well, that's just 1. The limit of the bottom, we just compute it using Squeeze theorem, that's equal to 1. So 1 over 1 is 1. And this finishes the proof. Okay? Again, you don't need to do this every single time. This is just so that you hopefully believe now this is a special limit. You actually already had an idea about this because you did it numerically. in the homework number one. But now we know, remember, numerical computations, these are just an estimate. You're doing an educated guess of what the answer should be, but you're not 100% sure. Now we are, okay? And this was a clever use of squeeze theorem. So, moral of the story. From here, what you need to know is what's written here above. You need to know these special limits. Sine of x over x, as x approaches 0, the limit is 1. 1 minus cosine of x over x, as x approaches 0, the limit is 0. And you need to know that these two limits that are here, they are both variations of the number e. Okay? All right, so close this. Let me do a couple of examples and then we are good. All right, so I guess, yeah, let me do it in a new tab. So let me just put here samples. Okay. Okay. So here we go. So find the limits. And let's do limit as x approaches 0. Let's do tangent of x over x. Let's do limit as x approaches 0 of sine of 4x over x. These were the kind of limits that you were investigating in the homework. And then let's do the limit as x approaches 0 of sine of 2x over sine of 3x. Okay. All right. So let me do these three examples, and then we will call it a day. Okay. So solution. Let's see for number one. So here the idea is that we want to use our special limit, but before we use the special limit, we need to do something. Why? Remember, first thing is you plug in. When you plug in 0, we get tangent of 0, which is equal to 0, and in the bottom we have 0, so this is 0 over 0. Okay, so something needs to be done. Okay, so the point is that you should realize that tangent is sine over cosine, so I can write this as sine of x over, let me do it little by little. So sine over cosine, that's tangent, all over x. So this can be rewritten as sine over x times cosine. Now, you should recognize that here we have the presence of the special limit, sine of x over x, as x approaches 0. We just need to modify this to be able to use it. So the idea is that we split this as sine of x over x times 1 over cosine. And now we can use the property that limit of the product is the product of the limits, provided they exist. Do they? Well, let's see. This one is equal to 1, special limit. And this one, 1 over cosine. So cosine of 0 is equal to 1. So this is also 1. So we can proceed. So 1 times 1, which is 1. Okay? So tangent of x over x, as x approaches 0, that limit is also equal to 1. All right, for the second one, we could do this in two ways. We can do it by using a substitution or just by looking at the special limit in, from another light or from another point of view. Let me do it that way because that's easier. So note, we know that the limit as x approaches 0 of sine of x over x equals 1, right? That's our special limit. So instead of calling it x, I'm gonna call it u, okay? So similarly, I could say, instead of putting an x here, I could say here u. Okay, it doesn't matter, just switch the x with the u. The point is that I want you to understand is the following. And the reason why I wrote u is so that we don't have the same x as we have above. is that this actually is telling me the following. Every time that you have the limit of the sign of something over that same something, they have to be the same, okay? If that something approaches 0, then this limit will be equal to 1. In this case, that something is our u, okay? So what do I mean by this? In this problem, our something, so the stuff in the argument of the sign is not x, it's actually a 4x, right? So if we want to use our special limit, we need to make sure that we match in the denominator, we need to have exactly the same as the argument. So we need to have a 4x as well. So we only have an x, so we are missing a 4. There's only an x in here, we need a 4, okay? And notice that the limit is as x approaches 0, true. But when x approaches 0, 4x also approaches 0. So I guess I'll say here, let me keep it as x approaches 0 here. And as long as the something approaches 0 whenever x approaches 0, okay? Which in this case, our 4x will approach 0 when x approaches 0, so that's good. In other words, all we need is to make sure that we have a 4x in the bottom. Now, when you're off by a constant, that's an easy thing to fix. So what do you need? We need to have a 4x down here. So this is what we had so far. So I need a 4. Okay, I'm going to put it. But remember, if you multiply the bottom by 4, you have to multiply the top by 4. Okay? So let me put it here, the top. So times 4. In other words, I went ahead and multiplied. Basically what I did was I multiplied top and bottom by 4. Why did I do that? Because I wanted to make sure that whatever I have inside the sign now matches with my denominator. Because if that's the case, we can use our special limit. Okay? So again, limit of the product is the product of the limit, but now this would be 1 times 4. So the answer is 4. As you know from your experiments in the numerical approach, right? From your computations numerically in homework number 1. And notice that, any number that you have multiplying the x inside the sign, you can play the same trick. Just multiply top and bottom by that number so that you can match the argument of the sign in the denominator, and then you can use special limit. That was that one. And then number 3, we're going to use a similar idea. It's just that we need to be a little bit more creative. So we have sine of 2x over sine of 3x. So I want to use the same idea as before. It's just that we have to be a little bit more creative because I have a sine of 2x. I'm going to rewrite this as, by the way, this is 0 over 0. Okay, so we need to do something. Sine of 2x over 1 times 1 over sine of 3x. And then, let's wonder what we need. For the first fraction, because I have a 2x here, that means that I need a 2x in the denominator. Okay, so I'm going to put it. I need a 2x there. But it was not there. So if I multiply in the bottom, I need to multiply in the top. So I'm going to put it here outside. Okay, I'm going to put a 2x here. Okay, so now for the other fraction, for the other one, I have a 3x here. Remember, it doesn't matter whether we have a denominator or numerator. Actually, the original one that we proved was x over sine, not sine over x, okay? So I just need to have a 3x on top, right? So let's do the same thing. So if I put a 3x here, then I will have to divide by that. So I'm going to divide here. Now, there is some redundancy here because you see those x's that we have red and blue in the outside, they're going to cancel. So I might as well borrow the one that we already had. In other words, the x that I had here, I'm going to put it here. Okay? In that way, I don't have to deal with that cancellation. So again, hopefully just make sure that you see the order in which I did the steps. So first I split it, right? And then the sign of 2x is on top, so I need a 2x in the bottom. I put it, but then I have to have 2x on top. So here is a 2, and here is a x to compensate that 2x that I put in the bottom. Similarly, I have a sine of 3x. I need a 3 in the top. I already have my x, right? Because of the first movement that I did. Now I need a 3. Okay, we put the 3. Here it is. Let me change the color. Here is a 3. But if you multiply by 3 there, you need to divide by 3 to compensate, right? And that's the second 3 that we have in the denominator. Now we are in business. So when we take the limit, this guy goes to 1. Special limit, this one also goes to 1. So the answer will be 1 times 1 times 2 over 3, which is 2 over 3. Moral of the story. So remark, notice that that 2 over 3 is actually this right here. So the remark is that when you have the limit as x approaches 0 of sine of ax over sine of bx, where a and b are numbers, we can play the same game that we just did here in this example, and the answer will come up to be a over b, right? Like the 2 over 3 that we had here. Okay, guys, so I think this was good enough. And for today, then, make sure that you understand what we did here. With this, you can now work on homework number 4. And so when coming on Monday, I'm gonna, as you have questions on any of the discussions that I had here, just go ahead and ask me, talk about it, and then we're gonna begin talking about continuity. We're gonna talk about continuity, and then right after that, we will have our first test. Okay. All right. So I'm gonna stop recording now.